Hey, let's start our discussion of heterogeneous diffusion, diffusion in heterogeneous medium by starting with a discussion on steric exclusion and hindered diffusion. So both of these come from the geometry of the pore and the size of the solute. So we will look at a membrane. So for the next few lectures, we would always think about a membrane with pores in this context. So here I've drawn a membrane and some pores. Now, if you look at the pores, this is where the solute can go through. So if diffusion happens, that's what happens. And if you look at the cross-sectional area of the pore, so this is the cross-sectional area of the pore. It's a circle. Let's say it has radius r. And if the solute are tiny or doesn't occupy any space, then you wouldn't worry about something called a steric effect. And then once you need to consider the size of the solute, that's where the steric exclusion comes into play. The steric exclusion. So it arises from the finite size of the solute relative to the pore. So suppose this is the size of your solute. And the solute, because of the size, it cannot approach the pore wall more closely than its own radius. So it effectively reduces the cross-sectional area of the pore available for diffusion. What I mean is if the radius of, let me put down radius of the pore is r, and then let's call radius of the solute. It's called a. So now we have a region which is distance a from, this is distance a from the wall, which are not accessible by the solute. So solute can only confine or can only diffuse in a distance or in a radius, effective radius, which is a r minus a. This is steric exclusion. So the available fraction of the post cross-sectional area is reduced, and we can express in terms of a partition coefficient. So we define partition coefficient, we call it K. So K is defined by the available area by the solute, which is pi multiplied by r minus a squared, divided by the total area of the cross-sectional area, which is pi r squared. And then you can cancel pi, you get 1 minus a divided by r squared. And then this is the partition coefficient. And then now you think about the concentration of the pore. So these are in the pore region. There is a pore. And the outside of the pore is, we call it bulk. Now let's zoom in a little bit. So the pore It's a pore. Now let's consider solutes with finite size. No, that's the where the solute can be within the pore. So it's the available space. It cannot getting closer to the wall than its radius. However, in the bulk part, it doesn't have such restriction. There's no wall that limits its place. So because of it can exist in a larger space than it can exist in the pore. So the concentration in the box space evaluated at the pore mouth. So it right on the boundary, right at the surface of the membrane, we would consider the concentration of the solute evaluated or let me put it this way, the concentration of the solute within the pore, right at the pore mouth. Would be less than the concentration of the solute in the bulk in the same physical location, which you can give it x equal to certain number. So if you give it the same coordinate, but just one is within slightly within the membrane, the other is within the pore, the other is slightly just out in the bulk part. At the same physical location, we would expect that there is such a difference in concentration is less than. So how much less? And this is given by the partition coefficient. So actually K equal to CA at the pore divided by CA at the bulk evaluated at the pore mouth. So this is how you connect the steric exclusion to the concentration in and out of the membrane. So this is steric exclusion. Let's look at the second factor for the hindered diffusion. So hindered diffusion is due to the hydrodynamic resistance. So it's related to hydrodynamic environment. So if you recall, when we discussed Stokes-Einstein relation, we had a Stokes law says, okay, if you have a sphere move at some velocity, we call it V infinite, but you can just call it V, it doesn't really matter. Then the fluid around it will give it a drag force 6 I mu A B. This is this for Stokes law. This is for an infinite medium. For an infinitely large medium. So that means the fluid around us, surrounding this sphere is so large that the sphere doesn't feel feel any boundary of the medium. There's no hard wall that the sphere can feel. And however, if you have another scenario which instead of infinite medium, the sphere is moving in a small channel, then the fluid environment around it are totally different from the fluid environment compared to an infinite space. And in this case, you would have higher resistance drug, higher viscous drug. Maybe it's a higher fluid drug, maybe putting this one. It's not, sometimes it's not only due to viscosity. Higher fluid drug, compared to infinite medium. So this is called hindered diffusion. And we right now we will discuss as some empirical way to estimate the hindered diffusion effect. Right now we don't derive from the first principle what's the hindered effect, because this is if you want to solve it analytically, it's extremely challenging, and we don't solve this. Here, our goal is to let you understand there is something called hindered effect. However, we can calculate the steric exclusion. This is something you can have a nice and a short formula. So this is good. So this is about what I would like to cover in this lecture about steric exclusion and hindered diffusion. Let me leave an exercise for this. So show that. To the partition coefficient K as A approaches to R, as the radius of the solute approaches the radius of the pore. What does this imply physically? And what might happen if A is larger than R? Okay, that's the exercise for this lecture. It will be a part of your homework.